Good morning, everyone. How many of you attended the keynote talk this morning about quantum computing? Oh, most of you. So you all know what the whys are of quantum computing. You're all excited about it, hopefully? Good. Yeah, first of all, thank you so much to the organizers for organizing this great conference and for inviting me to come and speak. It's really great to be in Chicago. I'm glad you guys brought the Danish weather also. It's good to make Europeans feel at home. Yeah. Maybe some bicycles also. So my name is Gwen, and today I will talk about how to get started with quantum programming. So Jessica told you what the purpose is of quantum computing. She showed you a little bit about like the Jupyter notebooks that are out there that can help you get started. I've prepared some coding examples in several different languages. There's a whole zoo of different domain-specific languages out there that will help you get started with quantum circuit programming. So I'm a software engineer and I have a physics background. I've been doing experimental quantum physics for about 10 years. And I was working on building quantum computers at Rigetti Computing for about a year and a half. And currently, I actually made a switch to biotech. So if you're interested in learning more about biotech, please come talk to me as well. I'm working at a biotech company called Perfect Day Foods. And we're creating animal-free dairy products using microflora. So that's also very exciting. So I'll start with a brief introduction to quantum computing, and then I will dive into several of these examples. So the best way to understand quantum computing is to understand some principles of quantum mechanics. So you've already seen at the talk, it's all about probability distributions, right? So this is a video of a tabletop galton board. I don't know if you're familiar with this. It's also called a bean machine, I think, where you basically have a bunch of beads that are led through a maze, a triangular maze of pins. And then at each pin, they randomly decide to go left or right? And then they end up in these bins at the bottom. And you can see that once you actually throw these beads through, you end up with this beautiful binomial distribution or normal distribution. So even though we cannot predict exactly what path each bead is going to take, we know where the ensemble of beads is going to end up. So this is overall what probability looks like on a macroscopic level. So now if we go to a more atomic level, so here you see these are actually measurement data from NASA, from the Jet Propulsion Laboratory at Caltech. And what you see here is called a Bose-Einstein condensate. So a Bose-Einstein condensate is an example of how a large number of atoms or particles, quantum behaving particles, can act together in a quantum mechanical way. So this is where you see basically this gas being cooled down to several tens of nanokelvin, which is a few nanokelvin, is almost absolute zero. And similar to when you are in a room and it's really cold, people start huddling together. That's what these atoms do in a quantum mechanical way. So they're all quantum coherent with each other. And this quantum behavior is fundamentally different from those beads I just showed you. So the beads, they show probability distribution, but these atoms actually behave in sync with each other because of something we call quantum coherence. This coherence is based on a phenomenon in quantum physics called the particle-wave duality. Are you all familiar with particle-wave duality? Have you ever heard this term before? Maybe, yeah. So this is what's kind of the mind-boggling thing about quantum mechanics, and this all started in the early 20th century in Copenhagen, where Niels Bohr came up with the model of the atom, but then soon they found out that electrons aren't just particles that are circling around in a nucleus. They're actually a probability clouds. So what you see here are electron probability densities of the hydrogen atom, in specific the first three s orbitals. So what this means is that as the quantum scale, every quantum entity can behave both as a particle and as a wave. And we found that this actually accurately describes nature using something called the Schrödinger equation. You can calculate this, meaning that an electron, for example, is just a wave packet of energy that can actually interfere with other electrons or with itself even. This phenomenon explains why you can have this thing as orbitals, because if you just have electrons circling a nucleus, there's not really any reason why it wouldn't crash into the nucleus itself. So the fact that at a quantum scale, these electrons start behaving as waves tells us that we have nodes and that we have these quantized energy levels. So each orbital has a higher energy associated with it, and it somehow looks like a ladder. So, and very important also to note is that on these nodes where you actually see like there's no color, you will never find an electron there. So this ladder is exactly what we use to create a qubit or a quantum bit. So we only use the bottom 2 steps of the ladder and use it to encode Boolean information, a 0 or a 1. However, because of quantum mechanics, the value of the qubit is not simply 0 or 1. It takes the value of a quantum state or a wave function. So it means that you can have this electron can have this discrete energy, but it also has this wave information such as phase. In very simple terms, it means it can be 0 and 1 at the same time, as you saw during the talk this morning. So you may be familiar with the analogy of Schrödinger's cat. Has everyone heard of the cat analogy before? Schrödinger's cat, dead or alive? Okay, about half the people. So this is what the quantum states look like in something called Dirac notation. So this tells you basically, this describes this wave, the wave function. So the idea of the Schrödinger cat analogy, so here you see this cute cat wearing an angel costume, which doesn't look very happy about. So the example Jessica used this morning is with a donut, a spinning donut, right? That it's 0, 1, 1 at the same time, or it's like coded and not coded at the same time. So in the early 20th century, when they discovered this theoretically, they had trouble like actually making sense of this, right? Because something is either 1 or it's 0. It's not 1 and 0 at the same time. So they came up with this analogy where, very cruelly, they put a cat in a box. This is a mental model. They didn't actually put a cat in a box. But you mentally put a cat in a box. You accompany it by a vial of poison. And then you make this contraption where there's a little hammer that smashes the vial if you connect it to a quantum system that decays, for example, a radioactive atom. So a radioactive atom can have this quantum superposition, this quantum probability where it's decayed or not decayed, right? So there's a probability of an electron decaying, and before it actually is measured, it lives in this superposition. So what you do is you couple that uncertainty, that state of the atom being decayed or not, you couple that to that little hammer, and then you close the box. Now, what this demonstrates is that when we don't measure a quantum state, it actually lives in this probability of being 0 and 1. It hasn't decided yet. So when you open the box, you decide, did it decay or not, this atom? If the atom decayed, you will find a dead cat in the box. If it didn't decay, the cat will be alive. So they extended this and said, oh, this cat is dead and alive at the same time. So that's, of course, a little bit of a silly analogy, but the point is that the wave function describes a probability density. In this way, it's very similar to those bees that I showed you in the beginning. While we know the overall probability distribution, we cannot exactly predict the value that this qubit or this atom will end up in until we actually take a look. So doing a measurement, a quantum measurement, is almost the same as throwing a bead through this galton board. However, while a galton board will always have this probability distribution engraved in its design, so in this triangular lattice, which makes up these pins, in quantum mechanics, we actually lose the wave information. So once we look into the box, the phase information of my wave is lost, and it just becomes a particle. So mathematics is hard, right? So physicists came up with another way to visually represent a wave function. So you may be familiar with the complex analysis. Have you guys taken like this type of mathematics before? I see some hands. Good. Yeah. So a wave, I can actually describe it on a complex plane, meaning there's this imaginary plane which lives in the square root -1 space. where I can actually encode this phase information. So a wave, as you can see here in this in this animation, it has a frequency and a phase. So it oscillates, and the phase tells you how much it's shifted on the x-axis. So this is how we represent a quantum wave. It has both these components. The sine and the cosine component lives in the or the cosine component lives in the real space, and the sine component lives in the imaginary space. So we use this to describe a wave, right? We just take a circle, and some point in the circle, you get this theta, which is the phase, right? So you see on the bottom right, you see this yellow, there's the phase is increasing, right? So now this doesn't actually include the value, so the 0 or 1, right? So what do? We add a third dimension, from which we get a sphere. So this is called the Bloch sphere. And this is how physicists like to represent a qubit. So this is not actually what a qubit looks like. This is just how it looks like in our head, such that we calculate with it and understand how we can program it. So there's a little animation here on the left of the Bloch sphere running an x pi pulse. So this is what Jessica introduced this morning as the NOT gate. So this is a quantum NOT gate. So what happens if I do a NOT is I actually rotate it. So this is actually a y. So it's rotating around the y-axis. And this basically changes the quantum states from 0 to 1. So this is how we do this quantum operation. And this x pulse is actually, can be different for each quantum system, but it's typically a microwave pulse. And I will explain later what that means. So now you can imagine I can do all kinds of rotations, right, in this Bloch sphere space. So here I have a little more complicated example where I do a pi over 2 over y, and then a pi over 2 in z, and then a minus pi over 2 in x. So this is basically when you are in quantum information, this is what you think about all day, is you think about how do I rotate this quantum wave function in parameter space. So let's go back to that cat example, right? How do we create the superposition state? So this is right, this Bloch sphere representation is really nice, is because you can really visually see what's going on, right? So it's this superposition of 0 and 1. In this case, it's alpha and beta are 0.5. So there's 50% probability. So there's normalized, so 0.5 divided by square root of 2. There's 50% probability that you will find the qubit in 0, and there's 50% probability you will find it in 1. Because when you see this sphere right now, so this is running what's called the Hadamard gate, which is a gate that rotates the qubit onto the equator of the Bloch sphere. So when we measure this qubit, we can only measure it in one axis, and we choose the z-axis. And as you can see, if I collapse this vector onto the z-axis, it's actually 0.5. But we cannot actually measure 0.5 in real life, so we either measure 0 or 1. So that's how you end up with this 50-50 probability. I hope this makes sense, right? So, and the other thing that happens is that, like I said, when you do this measurement, you lose the quantum information. So you literally collapse the wave function, is what we call it. So you end up with either 0 or 1 with 50% probability. So in quantum information science, or in quantum programming, we can then actually distinguish between quantum information and classical information, while the quantum information is what happens on the Bloch sphere when I still have my phase information, which typically happens in some sort of abstract space or in your head, in your circuit, before you measure it. And then whatever comes out in real life is what we call the classical information. And this manifests itself as well in these quantum programming domain-specific languages. So now, what happens if I have 2 qubits, right? So 1 qubit, I could do all these rotations. That's great. That's not really super useful, right? To actually scale up and do bigger quantum programs, you have to connect 2 qubits. And once you can connect 2 qubits, you can connect 3 qubits, et cetera, et cetera. So here's an example of a 2-qubit gate, a control X. I apologize, I have done a control Y actually in the animation, but you get the idea. It's just rotating around the 90-degree off axis. So the idea of a control X gate is that you take two qubits and you turn on an interaction between them, and I will explain later how that works in the hardware. But what you do is only if and only if the control qubit is in the one state, so pointing down on this block sphere, the target qubit will get flipped. And if the control qubit is in the 0 state, nothing happens to the target qubit. What I can do then, so this is, okay, this might be useful, right? This is some kind of if statement, right? If control qubit is 1, then flip target qubit. But now I can do something very typical of quantum mechanics, which is I can create something called entanglement, right? So what I do is I do the same operation on the control qubit as I showed before with the Hadamard, where I create this cat state, right? The 0 and 1 at the same time. And then I have a second qubit, and it has its own probability, right? So it does its own thing. But now when I actually run the control X gate, so I use my control qubit, which is in the superposition, as my control qubit, and I apply the CX, the control X, to the target qubit, what happens is that now they become entangled. So what that means, they're entangled means that if the control qubit, if in the control qubit I measure 0, I will also measure 0 in the target qubit. And when I measure 1 in the control qubit, I will also measure 1 in the target qubit. So their probability distributions become inherently dependent on each other. And this is what we call a Bell state. So if you look at papers or if you look at science, people will always refer to this as a Bell state. I will show you in the quantum programming example how to create a Bell state. And I'll show you that if you measure it, you will actually only get 0, 0 or 1, 1. You will never get 0, 1 or 1, 0. So how do I actually turn all of this theory into quantum programming, right? So there's a few things I want to be able to do. I want to be able to create and run these quantum circuits, right? All these rotations on the block sphere using these gates such as the identity gate, which basically means I do nothing. X, I rotate around X. Y, I rotate around Y. Z, I rotate around Z. Then I have all these control X, control Y, and I have a whole zoo of gates that are basically derived from this basis set. Then the second thing I need is I want some registers, some way to store and access the information. So I'm going to distinguish between classical and quantum registers. Obviously, I cannot have quantum registers on a normal computer, so that needs to happen in quantum hardware. But the classical registers then need to happen in regular hardware computers. Typically, these quantum programming packages or software development kits come with built-in simulators, which can both simulate running it against a real quantum computer or simulating like the actual wave function, so you can get the wave function information back. And some can actually be run on real prototype hardware. So, like I told you before, I'm an experimental physicist, and I've been working as a quantum engineer previously. So what is quantum engineering? It's where we take quantum physics and use it to create new technology. We apply the knowledge we have theoretically from quantum mechanics and apply it. So this is an example of a superconducting qubit device or a transmon qubit device, which is a way to create an artificial atom. So like I told you before, in atoms you have all this ladder, right? All these energy levels from the different orbitals, from the different harmonics, right, of these waves. Of electrons, so I can simulate that, or I can engineer that same principle in integrated circuits. So what you see here is a microscope image of such an integrated circuit. There's a scale bar on the bottom right. It's about 2 millimeters. And what I do is I basically take. Is anyone here familiar with resonance circuits, like RF technology? Just a few people. Okay. So it's a little bit similar to how RFID tags work. So, an RFID tag, it's basically a small radio. It's a radio transceiver, right? So, what you see these swirly lines. I've deliberately taken an example of an RFID tag that kind of looks like the chip on the left. Other RFID tags look very different. But these swirly lines are basically waveguides, so they're antennas. So they're swirly because they need to have a certain length to match the wave that they are picking up. And then there's a large capacitance. So what you create then is something called an LC circuit, where L is an inductor and C is a capacitor. The swirly lines are actually the inductor. So what happens is that they capture a current, and then by the principle of magnetics, you get a small magnetic field. And that magnetic field then gets transferred back to current, and then it oscillates back and forth between electric charge and a magnetic field. And then what you can do is you actually create something called microwave photons, which behave similarly as these electrons in the probability clouds. So you don't have to understand all of this physics, but I thought it would be fun to show the comparison here, because on the left you see it's like 2 millimeters, maybe a little bit more, and on the right you see the RFID tags are 20 millimeters, so they're not actually that small. The secret sauce here is, of course, that you have to cool this down to very, very low temperatures. So like I showed you in the second slide in the beginning with the Bose-Einstein condensate, to actually get quantum coherence to show its effects, you need to cool it down really, really cold so that all the thermal interactions with the environment do not disturb the quantum state and make it lose its quantum information. So this transmon qubit system that I showed you before is actually has been quite successful. And IBM Quantum, for example, has put some of these chips available in the cloud. So you can run quantum algorithms against these small quantum computers. So they have these two 5-qubit devices available to the public, so you can run against it. The actual specs are on the right. You can see something called frequency, T1, T2. I'm not going to go into exactly what those mean, but what they basically tell you is how long they can retain the quantum information. So even though these chips are really cold, right, and I actually have the quantum information intact, they still have problems with impurities in the system that make the qubits lose their quantum information faster than you'd like. So we're not there yet. There's still a lot of engineering to do to scale this up. But we can already start playing around with these prototype systems, which I think is pretty cool. So there's a lot, like I said, there's a whole zoo of domain-specific languages out there. I'm going to go through these 5 today. So please don't be offended if I didn't list your favorite language in here. I'm happy to chat about it afterwards and add some examples to the notebook. So the ones that I've been looking at is Q#, which has been built as a domain-specific language built by Microsoft. And it's sort of a mix between C# and F#. So if you're familiar with those languages, I would recommend starting in Q#. They come with an SDK, you can download it. Yeah, it's pretty cool. The docs are really good. Then there's Quill, which is from my former employer, Rigetti. Quill is written in Lisp. Are there any Lispers out here? No Lisp? Okay. Oh, yeah, there you go. Lisp is one of the oldest programming languages that exists. It's a functional programming language, and the person who wrote this is a Lisp enthusiast, so it's quite the community. But the actual backend works in Lisp and the simulator itself, but you can interact with it with Python, which is a little more friendly than Lisp. There's also Project Q, which is a little bit of a smaller project, but also similar, also Python. Then there's Qiskit, which is by far the most mature one out there. It's the one from IBM, so you can use Qiskit to run circuits on the hardware. It's also Python modules, and there's a lot of examples. So if you want to get started, I would recommend Qiskit if you're a Python developer. And then there's Cirq, which is a little more recent. It's by Google. It's similar to Qiskit and Quill. It's pretty elegant and easy to use. It doesn't have as much examples because it's not as mature. But I think like it looks really solid from an engineering perspective. So the examples I'm going to show you today are going to be running on this stack over here. So I virtualized everything in a Docker container. Do you guys work with Docker? Show of hands. About half the people here work with Docker. So Docker, you can run it either on a server or you can run it on your desktop. So I've specifically run this on my desktop. It's basically a virtualization engine where you can create Linux machines. So you can, like Ansible style, create install scripts. Binder is also runs on Docker and allows you to run Jupyter notebooks in the cloud for free. So that's really nice if you just want to get started really quick. In my repository, I've included a link to Binder so you can actually start running it. Then, of course, I'm using Python. Matplotlib, the unsung hero of data science. Qtip, Quantum Toolbox in Python. It's very nice. So all the Blocksphere stuff, animations that you saw were all created with Qtip and Matplotlib. So that's a really nice library to get started. So yeah, without further ado, let's go to the demo. If you want to code along or if you want to look at it later, the actual notebook, you can find it at this URL. So I'm just going to change my display settings. All right, can everybody see this? Shall I increase the font? Are you guys good? Increase it a bit? Okay. All right. So I'm just going to show you real quick what's going on here. So on the left, I'm not going to increase the font size because it's just logs. This is the notebook application. On the right, you see the Docker file. So I inherit from Python 3.7. Then I install some dependencies for all my examples. So Qtip, NumPy, SciPy, etc. Then the Q-Sharp engine runs on .NET SDK, so install all those dependencies. Then the Rigetti QVM was recently open sourced, so we can just straight up copy the source over to this Docker container. Then here I install these quantum packages. So I've got Project Q, PyQuil, which is the Python sort of like interface for Quill, Circ, Q-Sharp. Then, of course, dependency problems, so I install Matplotlib again. This is all for Binder. And then I install IQ-Sharp, which is like a .NET install. So for those of you who are C# developers, you'll be familiar with these commands. And then here I install some other stuff used for the demo. So yeah, so you can find this all on the repo. So yeah, now we go to the demo. So just fix this font size situation. Actually, one sec. Let's see, is this all right? Great. So let me just show you the root real quick. Oh, whoopsie, excuse me. So there's 3 notebooks in this repo. One is called animating 1-qubit gates. Those show all the source code I used to animate those examples I showed. So you can fix my mistake. And instead of rotating around the y-axis, you can now rotate it around the x-axis. I will probably push a fix for that later today. Then hello world, of course. We all start with hello world. And in this case, I'm not going to actually run hello world. I'm going to run H, which is the Hadamard gate, in these 5 different languages. And the fun thing is I can do this all on the same notebook, which I think is fun. And then I'm going to give a little more deep dive coding example, if we have time, of a quantum galton board. So the example I showed at the beginning, the galton board, I actually coded that in using Qiskit. And you can actually very, very much see the example there. So this is just to illustrate a little more how this works. All right, so I'm not going to go through this one because you've already seen the examples, but yeah, basically it will allow you to run all these examples. So I'm just going to close that. All right, everybody ready? Live demo time. I do have a backup in case it dies. Okay. So let's start. Do let me know if I'm going too fast or if you can't read it for whatever reason. Okay, so first let's install some or import some packages. Everyone here familiar with Python? Are the people here never used Python? Okay, I see. Okay, so you know, I'm going to assume some basic level of coding skills here. So I'm going to import some modules here. And this matplotlib inline magic command allows me to make plots in this notebook. So let's start. So we have these 5 languages here. These are just convenient links to the different parts. So let's start by just visualizing what the program is we're going to run, the hello world or H example, right? So I'm going to use Qtip for that. So I'm going to import the block sphere class and then the basis. So people familiar with linear algebra are going to know what this means. And then I import the Hadamard gate, which is called snot, funnily. Well, as not. I think S is probably a superposition or singlet or something like that. So let's run snot, as not. This is, so again, heads up to the linear algebra people, this is the matrix, a representation of this gate. So the basis is going to be 0, 1, and 1, 0, which encodes the 0 and the 1, and then every quantum operation is basically multiplying this matrix with the 0, 1. But we don't have to think about that because people already abstracted that away from us, for us, so that's great. So that's what you basically see here, right? So this is what you should end up with, this superposition, right? So you can see here it's 0.707, which is 1 over square root 2, right? So you're gonna see that. All right, so we start by just plotting it. So we're all familiar with this, or showed this in the presentation. This is what we want to end up, the qubit ending up in. All right, so Project Q. Project Q started a while ago at ETH Zurich. It's one of the earlier ones. It's not as mature, so I'll just quickly run through, but it basically is very simple, so it shows you very well what the different concepts are. So we start by importing main engine, which is my simulation engine. So this is this quantum simulator in the backend. I think in this case written in C++, I'm not sure, but basically what it does, it's just a linear algebra solver, right? And it helps you solve these equations here that I showed here, but it does so, and it optimizes. So if it has a huge matrix, and it needs to multiply that by a vector, it optimizes that and only finds regions in the matrix where there's actually values, such that your CPU is not working that hard, right? So now I import the operations. Let's import a Hadamard gate and a measure command. So this is the actual quantum measurement that I talked about, or basically throwing the bead down the galton board, right? Now create the engine. And now I allocate a qubit. So this is what we call this quantum register, right? So now I tell the engine, create a qubit for me, please. All right. So they did this nifty thing where they used the Python or expression to do their quantum stuff. So it's a decision. I really like explicit programming, but I think it looks really elegant, right? Okay, and then I flush this through the engine, which has a funny doc string if you look at it, and it says, flush the entire circuit down the pipeline, clearing potential. Okay, so I create this circuit and I flush it down the pipeline, and then it's going to give me some result, right? It's going to collapse the quantum state, and it's going to give me either 0 or 1. So let's run this a couple times. Oh, now I get 1. I get 1 again. Now I get 0, right? So you can hit this a couple times and you'll see. Okay, great. So now let's go to Qiskit. So Qiskit, this is going to be a bit of a bigger jump, right? So Qiskit is the more mature one. So they have these fun names, air and whatnot. I don't actually know exactly what the names are, but basic air is the backend that will allow you to run against the simulator. So here it's very explicit, right? So I'm importing the classical register, the quantum register, and a quantum circuit. And then I import an execute function. Sounds good to me. So now I do the same thing as I did in Project Q, right? I set up my quantum register, but now I also set up a classical register. And these actually have to be the same size. If they're not the same size, it's going to complain. Now I create a quantum circuit using those registers, so I initialize my quantum circuit object. And then I run so this is all pretty Pythonic, right? So I'm mutating this quantum circuit by running all these methods. So this H is the Hadamard, and then the measure, and it's going to run on my quantum circuit, on my classical and quantum register. So I do the Hadamard, and then I do the measure. So one cool thing that Qiskit has is that it can actually draw the quantum circuit for you. So you might, be familiar with this. I think Jessica showed it as well this morning, the sort of lane. So this is a way to visualize quantum circuits. So if you're familiar with maybe like classical, so like FPGA programming and so on, this is sort of a visualization of the flow of the data stream, basically the data flow through all these circuits. So here I have qubit 0. I don't know if you can see my mouse, right? Yeah, good. So I have qubit 0, which is the only qubit I have. I always start from 0, by the way. All of these languages, I start at 0. If I want to start in 1, I have to apply an X pulse first. I run it through the Hadamard, so I create the superposition, and then I measure it. So this little icon here means I measure it, and I dump the result into this classical circuit. All right, looks good to me. Let's run it. So now I get this big, complicated object back. But now if I want to actually see what it did, I use this method called getCounts. Here we go. So we ran this 1,000 times. So you see here. So I execute this against the backend, the QASM simulator backend, which is the sort of like quantum simulator. And here I can determine how many shots, so how many different like die rolls or how many beads, sort of. So let's do this 10,000 times. There you go. So I now have about half and half. So it's not perfect because it sort of simulates, you know, rolling the dice, and it's always going to be a little bit off, but this sort of matches what we expect, right? Mm-hmm. Sorry, can you repeat the question? No. So this is all Docker. This is basically my talk should have been called "How to Program a Quantum Computer in Docker." Yeah, this is just all because the reason why I'm not running it against the real quantum hardware is because it takes a while. Like you usually get added to a queue, and it takes a while before your program actually runs. So that's not really feasible for a demo. But yeah, you can actually run this against a real quantum computer if you want. I'm happy to include more examples for that if you're interested. So yeah, this is just running against a simulator that's running on my classical computer. By the way, if you're wondering, so I talked to some people about this who are working on this on these backends. If you have like a 16 gigabyte RAM, you can run comfortably until like 26 qubits. So that's pretty good already. You can make like huge programs. So I'm just using like 1 qubit here, so that's pretty fast. So for the sake of learning, it's fine to just use a simulator. So now I'm going to use a different backend to actually get the state vector back. So this gets me this block sphere representation back, and it looks like what we expect, right? So that's useful. Okay, so now let's go to Quill from Rigetti. Quill uses something called a QVM as the backend, similar to what the Qiskit QASM. So this is the thing that's written in Lisp. So I import this class called QVM connection, which allows me to connect to the server. This is really convenient because then if you're running against a real CPU, you just swap out this connection for the QPU connection. And then we import the program, and then we import some gates. And then I start the QVM in a subprocess, and then I can run it. So it's a similar, it's a little bit different syntax. So here I actually have a list. So every program is a list of instructions. And I run that against the simulator, and then I just get zeros and ones back. So this is a little bit different, right? So as you saw in the Qiskit simulator, I just get the counts back, while in Quill I actually get the one-by-one results back. So that's, again, this is a design decision. You sort of lose information if you just get the results, like the sum back. But one can argue that it might not be that relevant. Maybe it is, depends on what kind of research you're doing, right? So if I want to get the sum, I can still do that. So 498, so that's about half again. And then I can also get the waveform back. So Cirq, that's the Google quantum programming language. Same thing, I start a simulator. So you'll see all of these things have this kind of stuff in common, right? There's not much you can really change about that. They also have something called a grid qubit. So they actually take the topology of the computer into account, the quantum computer. And then here I use this class method from ops, and I pass a key. So the result, I'm going to come back, it's going to be tied to this key, which is, I think, pretty useful. So then they have this cute ASCII simulator or ASCII representation of the circuit. And then I'm going to run it. So yeah, so circ is going to just straight up dump the bit string. So it's just going to give me back zeros and ones, similar to a quill, except that it just returns a string and not a list of lists. And yeah, if you do want that list of lists, you can still get it, and it returns Boolean values. So instead of 0. So yeah, not many differences here. So Q sharp. So this is going to be fun. So now we're actually going to change the kernel. So this Docker image installed, like I showed you in the beginning, it installed the .NET and all that stuff, and then it installed this backend for Jupyter. So I can click on Q sharp, and then it starts actually switching the kernel, and this takes a while, so I'm just going to run you through the code. So Q sharp is by far the most verbose one I've seen so far. The advantage of that is you can be very specific. You can really define what you get back. So as you saw in the other examples, it sort of pre-cans the notion of what you want back, right? So in Quill, you get the list of lists. In Qiskit, you just get a dictionary with some of the results. And then here, I can decide what I want, right? So I can define this operation. Then I create a mutable R in which I will store the qubit results. And then I can just do both, right? So I want the number of ones, and I want to have all the results back. So a list, basically. Then here I'm gonna go and do a for loop. So from 1 to the count a number of tries. And I'm going to run this Hadamard gate. So this is the hello world we're trying to do. Then I run this dump machine, which shows the current waveform. And then I actually measure. So M is my measure instruction. And then I add it to the result. So this is like it adds the result to the array. And then here I count. So this is just all under the hood kind of stuff in the other languages. But here I have to explicitly define it. And then I reset all the qubits before starting over. So yeah, so I ran this, and now let's actually simulate it. So I run it now for 10 counts. So let's increase this number maybe to 100. There you go. So yeah, so that's an overview of all the languages. I'm running a bit short on time. We have about 8 minutes left. I will quickly show you the quantum galton board, and then we can go to questions. Does that sound good? Great, thanks. All right, so galton board, triangular maze of pins. So it's basically a tree. Each node takes so I'm going to visualize this in a graph. Each node is a qubit. Each node takes a Boolean value, which indicates whether the ball should pass on the left or right. Okay, so 1 means it goes to the left, and 0 means it goes to the right. So again, I import my Python, scientific Python friends, PyLab, NumPy, Pandas, NetworkX, which allows me to create this graph. So I'm just going to start real simple, just with 1 node and two leaves. So I'm going to use Qiskit because then I can actually draw. So this is my quantum circuit. I don't have time to actually explain what this does. But in really sort of brief terms, it makes a superposition for the first node. So it puts this node, this qubit into a superposition of 0 and 1, which means it's still undecided. And then I do 2 of these entangling operations. So I put this in Hadamard, then I entangle these 2, and I entangle these 2, and then I measure these 2, right? So you can imagine what then happens is that I get a 50-50% chance of it going left or right. Okay, so this is what the circuit looks like. I put in barriers just to make it a little easier to read. All right, so this is what I get. So it gives me the bit string, 0, 1, 1, and 1, 0, 0. And it actually starts counting from the right. Okay, so this is actually the root node. And these are the leaves. So this is Q0, Q1, and Q2. So keep that in mind. So as you can see here, it went to the right, and here it went to the left. And it's 50-50, so that's cool. So I can also get the state. And I can do something called plot state city. So this is a way to visualize these probability distributions. And what's also cool is now I can find, based on this state vector, I can actually see how many possible paths there are. So you can imagine some kind of application where you take a graph, some arbitrary graph, and you do all these entangling operations, and then you calculate the state vector, and you can just calculate the number of paths instead of doing like depth first search or something like that. I haven't actually done this. If you're interested, let's chat. So real quick, let's scale it up one level. So now let's make this 2 levels. So now I have 3 nodes that I have to put in the superposition. So I'm going to make 6 qubits, and I'm going to draw that circuit. So this is what the circuit looks like. Again, there's 3 Hadamard gates, Q0, Q1, Q2, and I do all these entangling operations. This is called a Toffoli gate. It's a CC naught or CCX gate. And I'm going to measure that, and I get the state vector back. So again, linear algebra, blah, blah, blah. And see, I got 8 possible paths. And they all have to end up in these bins at the bottom, these Q3, Q4, Q5. So I have 8 possible paths to go down to these bins, and that makes sense, right? So you have 1, 2, 3, 4. Anyway, I have to go through this. Okay, so these are all the bit string possibilities. Now I'm going to do a little bit of massaging, data wrangling, to get the count per node. So here you see Q4, Q3, Q4, Q5. So there's 2 paths to get to Q3, 2 paths to get to Q5, and 4 paths to get to Q4. And they all occur with equal probability, so now that's count per node. And you see that, oh, wow, I actually get more hits in the center, which is kind of looks like that distribution I showed in the beginning. So yeah, let's go back to the presentation. There's some more resources here if you're interested. Will Zhang, a former colleague of mine, is teaching a course at Stanford. There's a bunch of resources on there, lecture slides. He explains everything really well. QuantumMadeSimple.com is very cool. It's not specific to quantum computing, but if you're interested in learning more about quantum mechanics and how atoms work and all that kind of stuff, go there. Then there's this website called Quark, which is really cool for actually creating all these quantum circuits that I showed you with those lines, and you can evaluate quantum circuits, and it shows you the states and the probability distributions. Then there's also this demonstration on Wolfram. It's a very long URL, single qubit quantum gate on a Bloch sphere. It's basically the same as the notebook I showed you in the beginning, where you animate the quantum gates. Except now it's like in an app, so you don't have to run any notebook or anything. So yeah, thank you so much for your attention. It was really fun to be here. Special thanks to these 3 folks over here. Follow them on Twitter if you're interested in more about quantum computing. And yeah, I'll take questions now if we still have some time. Maybe 2 minutes. Thank you.